Hello, welcome to today's YouTube video. Here's the agenda for today. I'm going to be talking about a scikit-learn implementation of the EM algorithm with the Gaussian mixture. Second, I'll be talking about gating intuition into the EM algorithm. Third, the mathematical theory behind the EM algorithm for GMM. Fourth, its implementation. Fifth, explaining major parts of the EM algorithm with respect to NumPy. Six, look at the EM algorithm again with the knowledge that we gained from five. And then seven, experiment with parameters and see how that affects convergence. So we did a scikit-learn implementation before. I'm going to be going over it quickly one more time. Some of the major ideas for this video is going to come from probability. So we're going to see that in order to implement the EM algorithm with the GMM, we're going to have to know the Bayes theorem, law of total probability, ideas from covariance variance, the multivariate normal distribution, and then the maximum likelihood estimation. So here's a scikit-learn implementation. You could see that there's three clusters basically that are occurring here. Um, we fit the Gaussian mixture, fit, then we predict the labels of the clusters, then we predict the probabilities, and then we basically graph it. Okay, so that's basically it. Now, we see kind of the final version of this, but we'll see later on that basically we have to initialize like parameters, right? So it's not like where the mean, for example, the mean is going to find its way here automatically. It's going to have to go through multiple iterations, right? And then we're going to capture a mean that describes this respective cluster, and that one, right? But we'll be going through that. So this is a nice implementation and it's quick. It doesn't show the mechanics or the machinery behind the EM algorithm and the GMM, but this is what you would want, right? You wouldn't want to see every detail, especially if you just want to get to a solution. So here's a saying that's pretty much sums up what the EM algorithm does, and it's by an American statistician by the name of Larry Wasserman. The EM algorithm lets you pretend you have complete data, estimate what's missing, and then optimize as if your guesses were true. Okay, we'll be seeing this. To have that in the back of your mind is pretty useful while we go through some of the steps. This is a high-level view of what the EM algorithm does. Now, in the EM algorithm, we've got something called latent variables. And what are they? They're hidden or unobserved factors that influence the data. So in the Gaussian mixture model, you're going to observe 2D points, and they're generated from multiple Gaussian distributions. Okay. First, you don't know how many Gaussians there are. And second, more importantly, you don't know which point came from which distribution. Point meaning the data point. Okay. We see in this example that all the data points are assigned near these means. Okay, but we don't know where each of these data points would fall in what cluster. So that's kind of what the objective of EM algorithms are, right? So each point has a latent variable, it's cluster membership or component assignment. Um, those those terms are used interchangeably, cluster membership and component assignment. Okay, so I don't want people to worry too much about when they hear one or the other. They're both pretty much synonymous. So real life analogy could be, say, imagine students take a test. You observe the scores, that's the data, and but you don't observe their intelligence or their motivation. So those unobserved factors would be latent variables. So the EM algorithm helps estimate both the latent variables, which is in the E step, and then two, the model parameters. So what exactly is missing in the EM algorithm for GMM? So in the expectation maximization algorithm for GMM, Gaussian Mixture Models, the missing data are the latent variables, specifically the component assignments for each observed data point. So component assignments, clusters, like what are they exactly, right? We have to distinguish between what's observed and what's missing. Okay, so we observe the data points x1, x2 to xn, and we don't observe the component or cluster labels. Okay, and then each zi here is a latent variable that indicates which Gaussian component generated xi. It can be represented as a categorical variable, 1, 2, 3, and whatnot. In our scikit-learn implementation, we saw 3. Okay. Why is it missing data? So if we knew the values of zi, we could directly use maximum likelihood estimation on the complete data log likelihood, right? So it's log p x z conditioned on theta, which are the parameters, okay? But since zi is missing, we instead maximize the marginal likelihood of the observed data, okay? And this is the multivariate normal distribution. This is something, this is like a weight, right? And we'll be seeing that a little bit more clearly later on. So how does the EM algorithm fill in the missing data? So it's estimate the expected value of the missing latent variable, right? That is compute the responsibility, RIK, the probability that data point xi was generated by component k. So the probability that zi is equal to k conditioned on the data point and the parameters, okay? And that's something called a responsibility. This pi k multivariate normal distribution, xi is conditioned on mu k and the covariance matrix k. Okay. So we use the responsibilities to update the parameters, the model parameters. Okay. Um, so xi is the only, this is a summary table. Xi is the only thing that's observed, which is a data point. Zi is missing, right? That's the component assignment or cluster membership for xi, right? In the scikit-learn implementation, we saw that there were 3. Pi k is the mixing coefficient for component k. You could call it a weight. Mu k is to be estimated, mean of the Gaussian component, and then this covariance matrix K is to be estimated as the covariance matrix of the Gaussian component. So the EM algorithm fills in the missing labels Zi probabilistically using the current parameter estimates, then uses those soft assignments to improve the parameter estimates, iterating until convergence. So what that means is basically we start off with something like a guess, right? We have these ideas of what these components should be, like pi k, mu k, and the covariance matrix k. We give some kind of guess, and then after each iteration, it comes closer to the true estimate. Okay. And then basically it's assigning these missing labels, these data points to these labels. Okay. What cluster membership that this particular data point will fall into. Okay. So I did mention that, like, in order to understand this, that we do have to know maximum likelihood, which is something that's going to be explicitly noted earlier. But we also need to know something called the multivariate Gaussian probability density function. Okay, so this is basically what we're going to be using in the likelihood, right? As the likelihood function so that the iterations converge. Okay, we're going to use this. Okay, and just a quick note, I have a video on this, but here's a brief review. Okay, so the xi is an element in the real number line to the d dimensions. the ith observed data vector with D features, okay? Mu k, mean vector of the kth Gaussian component, covariance matrix of the kth Gaussian component. This is the determinant of the covariance matrix, a scalar measuring the volume scaling of the Gaussian. Recall, I mean, I'm not sure what your backgrounds are, but in linear algebra, this has to be greater than zero, the determinant, in order for this to be invertible. Okay, so that's something to be noteful of. This is the inverse of the covariance matrix. D is the dimensionality. Xi minus mu k transpose of the vector, resulting in a 1 by D. And this is Mahalanobis distance squared, which measures distance accounting for the covariance. Okay, and this is an outer product. Okay. So what exactly is the expectation maximization algorithm? It's an iterative method used for finding maximum likelihood estimates of parameters in probabilistic models, particularly when the model involves hidden variables. In the case of GMMs, EM is used to estimate the parameters of multiple Gaussian distributions that describe a given set of data. Okay, so these are the major components we talked about previously. K is the number of Gaussian components. We saw in our implementation that there's three. Pi k is the mixing coefficient of each component. We could call that a prior probability, right? And mu k is the mean of each Gaussian component. And then the summation k is the covariance of each Gaussian component. Okay. So what is the goal of the EM algorithm? The goal of the EM algorithm is to maximize the likelihood, okay, of the observed data by estimating the parameters theta, pi k, mu k, and then summation k, which is the covariance matrix that best explain the data, right? So we've got this maximum likelihood estimation formula here. And the goal is to maximize the log likelihood, okay? So we've got this here, okay? The summations of multivariate normals weighted by the mixing coefficient, right? We take the log, okay? N is the number of data points, K is the number of components, pi k is the mixing coefficients, which should sum to 1, right? The multivariate Gaussian probability density evaluated at xi. So when we loop through this, we go through each data point. We're going to go through x1, x2, x3, and whatnot. So that's the way to look at it. N xi condition on mu k and the covariance matrix is the multivariate Gaussian probability density evaluated at xi. And then theta is finally the parameters that we optimize, right? Pi k, mu k, and the covariance matrix K. So again, the intuition, it's basically to calculate the expected value of the latent variable given the observed data, right? And then the maximization step, we update the parameters of the model by maximizing the expected log likelihood. And here is RIK, which is a posterior probability, okay? In the E step, we estimate the posterior probability that each data point xi belongs to each Gaussian component k. These are the responsibilities denoted by R subscript ik, which are the probabilities that data point xi is generated by the kth Gaussian component, okay? So this is a posterior probability. And then obviously I've shown the normal, right? And then k, pi k, and then k. Okay. So we've got this in the E step, okay? In the M step, these parameters pi k, mu k, and the covariance matrix k are updated to maximize this expected log likelihood, right? The updates are based on the responsibilities RIK computed in the E step. So the mixing coefficient pi k is updated as the average responsibility. We update the means by weighted average of the data points and then the responsibility, right? And then we update the covariance matrix for the kth component. And when we do this, EM algorithm iterates, right, between the E step and the F step until log likelihood converges or changes by a small amount, okay? So convergence is kind of the key here, right, in order to optimize our parameters. So again, summarizing the algorithm, we initialize the parameters, we calculate the responsibilities for each data point, we update the parameters, and then we repeat until convergence. The mixing coefficient here is basically saying before I see any data, I believe that 30% of the time the data will come from Gaussian number 2. Okay, that's just an arbitrary number, but it's basically making some kind of estimate, a prior estimate, right? A responsibility of the posterior, okay, is now that I've seen this data point, there's a 70% chance that it comes from Gaussian number 2. Okay, so that's the prior and the posterior. For those familiar with the Bayes theorem, that should ring a bell. Okay, the posterior and the prior. Um, and that's what I'm going to be discussing now. Okay, so in the Gaussian mixture model with k components, each data point xi is assumed to be generated from one of the k Gaussian distributions. The probability of observing xi is given by the law of total probability. Okay, so this is the law of total probability. If we had two mixing components or two Gaussian components, it would be pi 1 times the normal distribution of x1 conditioned on mu1 covariance matrix 1 plus pi 2 times the normal distribution of x2 conditioned on mu2 covariance matrix 2. Okay, so that's how I would expand it. Okay, expand this term, right? So pi 1, I'm not going to write the whole thing out, but x1 mu1, this is not coming out well. 1. Yeah, it doesn't come out well, but you see what I'm saying. Basically, we're expanding this out to how many components there are or clusters. In our implementation, we saw 3. Okay, so we would expand it out to 3. Okay, so that's the law of total probability being used here. So here, again, it's the mixing coefficient representing the prior probability, okay? And then this normal multivariate distribution is the likelihood of xi using the kth Gaussian distribution, okay? So there's going to be, in our implementation, there was 3. We're going to be working with 2, and we'll see that shortly. So the responsibility, okay, if we were to express this in using Bayes' theorem, is the posterior probability, okay? So we know that probability RIK is equal to the probability of ZI is equal to K, what membership, what cluster, conditioned on the data point 1, okay? And then we do probability of X1, Z1 is equal to K, times probability of Z1 is equal to K, divided by probability of X1. So if you look at this, this is the Bayes theorem, right? We've got our posterior probability and our prior probability, okay? And if we were just to substitute the Gaussian terms, we would get this term, right? We've got the prior probabilities here, the mixing coefficients, the normal multivariate, and then the law of total probability, okay? And if we say that there's 2, we could expand the term out to probability 1, this is the first cluster or responsibility. And then we do the mixing coefficient times this multivariate divided by the total probability, the law of total probability, right? That uses pi1 and pi2 and its respective Gaussians. And the same thing with Ri2, right? And the law, what it ensures basically is that the Ri plus Ri2 is equal to 1, okay? Here's an algorithm implementation in Python. Before I actually start with it, though, I do want to make a point that in this example, I'm using covariances that are 0. I'm hoping this works. And this will actually affect convergence. Okay, so I want people to keep in mind. I know that we're working with a lot of concepts here in this video, but it's important to keep these things in mind, right? That how these probability concepts are kind of working in in the math and then also in the overall theory, okay? But we've got these covariances that are 0. We've got unit variance. Basically, if we run something like this, we see that the clusters are pretty much different. I mean, they're pretty well separated, okay? And the reason why is because that the covariances are 0. And we'll see how later on when we play with these numbers, these covariances, how that will affect how well separated these clusters are. So there's quite a few things to be thinking about when you're working with something like this. Now I'm going to run the code, just a little brief overview, okay? We've got k is equal to, that's number of number of clusters, right? Number of samples and number of features, right? These are the rows, these are the columns, okay? We've got weights, right? We have to initialize, okay, this loop and this code, okay, in order to get it started, right? Because I mean, we have to have these things called priors in order to get the work started, right? And then later on, after each iteration, these things will update. Okay. We've got this EM loop, right, where we start off with the responsibilities is equal to NP zeros. This here is an initialization, right? Range 10 is the number of iterations. Range K here is the number of clusters, okay? And we assign weights times the multivariate normal PDF, right? And then we get the means I, covariance I. Remember that we have to take one data point at a time. Okay, and then we get the responsibilities. In the M step, we start updating the covariances, the weights, and the means based on the responsibilities. Okay. That's a quick overview. I'm going to be going over the NumPy implementation, exactly what it's doing. Okay. We use this NP einsum as an outer product. So recall in the math that we were looking at earlier, if we look at this here, this is an outer product, right? Um, and this will end up becoming a scalar, by the way, which is a single number for those that are not familiar with the technical terminology. Okay. So there's the math. And then we have to implement, if we want to do this from scratch, we have to implement it in code. And that's what we're doing here. Okay. What you could see is this NP new axis times X. We basically have to rearrange the dimensions. Okay. And I'll be showing this very shortly, but I'm kind of giving you the overall high level view of the code, right? We want to update the means and the covariances and the weights in the M step, right? In the E step, we take care of the responsibilities, okay? And then when we run it, which is there's two, we get this. Wait, what happened? So I apologize. So after we run it, we should get this, okay? So these clusters are really well separated. That's because the covariances are basically zero. Another point I want to make is that like looking at the dimensions, okay, when like I said, we're going to be going over this shortly, but the mean shape is 2, 2, right? And the covariance shape is 2, 2, 2. It has three dimensions, okay? Um, we see that here. We've got two rows, two columns, and then two matrices, okay? So here are the key NumPy concepts in the EM algorithm that we just saw, right? We saw broadcasting, where we saw the responsibilities um, times where we reshape the responsibilities, right? And then we multiply it by X, enables weighted sums, right? Without explicit loops. We normalize it, summing to one, right? So we keep probability summing to one per data point. And then we use the outer product with NP sum, efficiently calculates all the outer products. And then we sum weighted values over all samples. So axis is equal to 0, sums across columns, axis equal to 1, sums across, wait, so I'm sorry, axis equal to 1, sums across columns, and then axis equal to 0, sums across rows. So we see this. I mean, we see that we have to take care of this x minus means I, right? We saw that in our multivariate normal formula where we have to multiply this by the inverse covariance matrix, right? Um, and then the transpose of that, right? So we're doing this outer product here, okay? Going back, this right here, okay? So we have the responsibilities times this difference summed by RIK, the responsibility, divided by the sum of RIK. And that's what we're doing in the code right here. For the covariance matrix right here, okay? NK is the responsibilities here, the sum. So these are the NumPy commands that we would need to know, right? So what's NP new access? It's basically just reshaping the data. So I'm going to go through a couple of examples, quick examples here. We see that this is 3. It's one dimension, okay? If we reshape it here, we get a column, okay? Let me show you. I think it's a good idea when you do this to just follow the dimensional transformations, right? So this is one with 2 dimensions, okay? This is also 2 dimensions. Oh no, it's not. right? It's the same thing, this NP new axis and reshape, where we see the columns. And this is just the row where we could use this. We reverse this to 1, -1 instead of -1, 1, right? Column vector here, -1, 1. Okay. Now, here's something that we do to transform it into 3 dimensions, okay? You're going to see something like this. And this is an array with 3 items where each item is a 1 row, 1 column matrix, okay? And we look at the shape, 3 dimensions. So what we're doing in order to do these manipulations here, I'll show you right here. What we're doing is basically we're transforming. We know this is a 4 by 2 matrix. We need to multiply the responsibility times X, right? So we need to shape this, say, if this is a 4, into something that we could do, we could multiply by to get to 4, 2, right? So this is going to have to be 4, 1. It's 4, 1, right? So 4, 1 times X, which is 4, 2, it's going to be a 4, 4, 2, right? So it's 1. This is being multiplied across this and this and this, right? And then we're going to get a 4, 2, right? If you don't believe, let me just show you, like multiply the two for the first two. 0.1 times 1 is 0.1. 0.2 times 3 is 0.6. Okay. So that's what broadcasting is actually accomplishing, and that's what's part of the code, okay? And then if I multiply, like I said, I multiply by x and I get that. Okay, so then the second thing is normalization. Okay, and we have these responsibilities, and then we divide by responsibilities. Here it's pretty easy because I mean it's just going to be 1. It's going to just be the same thing. Why is that? Because they equal 1. 0.6 plus zero point 0.4, zero point 0.2 plus zero point 0.8. Okay, so it doesn't happen in our code above, but it happens here. And here is finally the outer product, okay? So we got x minus mu. We get this diff thing, and then we do this outer product, and we get this. And this was for our covariance matrices, right? Let's just look. Yep, here. Oh, I did this here before. And then finally, the summation, where we take the gamma 0.6, 0.4, we convert this to 3 dimensions, then we multiply it times this outer product here, and then we get the covariance. Um, right? Weighted covariance. We're summing here to get this, right? 0.15 plus zero point 0.1 is 0.25. 0.45 plus zero point 0.3 is equal to 0.75. 0.45 plus zero point 0.3 is equal to 0.75. 1.35 plus zero point 0.9 is 2.25. Okay. It should make sense, like where if you you get a covariance matrix with this makes sense. This is what it should be, a 2 by 2. Okay. It's always important to check dimensions across when you're doing manipulations because it's really easy to get lost in terms of what dimensions you're at and whatnot. Okay. Um, Thankfully, scikit-learn has got an implementation that takes care of all of this. But for those that want to actually learn the step-by-step technical detail, it's important to keep track of those things. So here's another example of outer product and summation, right? Just a step-by-step, again, to kind of review what we've just done. We've got 3 samples, 1, 2, 3, 2 features, 1, 2. Okay, so if we take the shape of this will be 3, 2. We've got a mean component, right? Remember, we have to initialize uh, before we run the EM algorithm because we don't know where to start. After each iteration, the means will update, right? But we need starting points. Responsibilities for 3 samples towards this component. We've got this. The shape is here, right? It's one dimension, okay? If I do x minus mean here, we get 3, 2, right? It's going to be the same thing. Then we take the outer product, right? And it's going to be 3, 2, 2. If we reshape the responsibilities, which is one dimension, to get it to 3 dimensions, we would do this R colon, comma, NP new access, comma, NP new access 311. Okay. Then we would take each element-wise multiplication, right? The R weighted times the outer products. And we would get 3, 2, 2, right? Because this is the one with 3, 2, 2. This is 3, 1, 1, but we would get what's bigger, right? And then we sum across the samples. Axis is equal to 0 divided by R dot sum, and then we get 2, 2. Okay. So you could see kind of the step-by-step approach to get to the dimensions of a covariance matrix and get to the covariance matrix. Now, let's go through the EM algorithm again. This time with some comments. And we're going to go through this basically knowing the important steps that we just went through with NumPy. Okay, so we generate a synthetic data set. Like I mentioned, the starting parameters, we need them, right, in order for this loop to even begin, okay? We stack these two, we create something called X, which is our data, okay? And like I said, we initialize it, right? We set up K is equal to 2, number of samples, number of features, is the shape. This time we put in max iterations, right? Because we want to know how many times we want to create a loop that basically goes through iterates and then maximizes the log likelihood, right? The tolerance, which is basically a convergence threshold. We've got the mixing coefficients, basically 1/2 here, right? Because we've got 2. So 1/2, 1/2. The means, we basically choose something randomly. right? Some number from X, okay? And then we take the covariance matrix, and we add a little noise to it, okay? If you saw my earlier video on introduction to the EM algorithm with missing data, we saw kind of this whole issue that could kind of occur if um, the rows are or the columns are dependent, right? So adding a little bit of a noise term to the data, it might prevent from being dependent, and then thus like your algorithm won't work because matrices are not invertible, which is a very important key feature um, to the multivariate normal distribution and hence towards the log likelihood. And then we get the covariance matrix, like I said, and then the log likelihoods. Okay, we want to count each iteration, or we want to store the values for each iteration. Here's the iterations, right? Like I said, we want to initialize the responsibilities. That's we've got zeros matrix, but this is going to be filled in after each loop, right? And I mentioned basically earlier that this is the formula that would be using. The weights here is the mixing coefficients. I use that interchangeably. Here are the responsibilities, right? And the responsibility ratios, right? Here's the log likelihood. So the responsibility sum, and then I append the log likelihoods, right? We're summing this term, okay? So if iteration is greater than 0, and then this difference is less than the tolerance, right? So this is the log likelihood on like the first iteration and then the second iteration, right? Or I'm sorry, this is the first log likelihood and this is the second log likelihood, right? And then, I mean, it's basically like a lag. And if it's less than the tolerance, then it'll converge, okay? Um, Here are the updating the parameters using the responsibilities. Obviously, K is 2. So we're going to update the means here, right? With what we discussed with the NumPy. We're going to update the covariance matrices. Here again, I add like a little small value for numerical stability. Remember, yeah, I mean, so I just mentioned that with the dependent possibility of dependence in the columns, and then the updating the mixing coefficient. If I do this, it works out perfectly, right? It's separated well and it converges on the third iteration. Okay. Now, what if the covariances were different instead of 0? And that's the final point that I want to make in this video. I'm not going to go through all this, but you're going to see that we've got this convergence. I mean, prior we saw it at 3. Here it's at 4. I mean, still at 3. Um, because the covariances were 0, right? But what if we were to increase the covariance? Meaning that the data points are moving between X and Y in the same direction. Okay. There's a correlation. I mean, people are more familiar with the term correlation than covariance, but correlation is just basically covariance weighted by the standard deviations of X and Y. You see that this dependence, okay, creates like not clear a not clear structure between these two um, clusters, right? There's a dependence. It seems more and more dependent. Okay. And if we were to like increase the variance, I mean, it would basically, things would change, right? Let's just keep this to 1 just to show you. But you could see if the variance, if the covariances are higher than 0, there's a dependence that develops in the structure. And the amount of iterations for it to converge increases dramatically at 40. Here it's at 40. Okay. So that has implications as to like how well your algorithm works and like whether you could distinguish uh, between clusters or cluster assignments, right? So that's going to wrap it up. Thank you very much. I'm going to put the notebook up on GitHub. Hopefully, you could go through it on your own, and I hope you learned a lot this session. Thank you, and I'll see you in the next session.